Hello, welcome to the playlist of videos on essential statistics for data science. I'm Hemakumar Kasala, and in this video I'll introduce you to two important discrete probability distributions, namely the binomial distribution and the geometric distribution. Let's understand the context behind these topics and subsequently the requirements, underlying concepts, mathematical equations, and their usage with some real-world examples. It is recommended that you go through the above two videos in order to understand the underlying concepts discussed in this video. But it's not mandatory if you are already aware of the basics around probability distributions. Let's get into the video. Two more commonly encountered discrete probability distributions are one binomial distribution and the other geometric distribution. To learn more on discrete probability distributions, please click the following link. Imagine an experiment that involves examining the RH factor in the blood samples of individuals that undergo the test. The study could be aimed at arriving on the probability of observing X number of RH negative samples in a sequence of n blood samples tested, where X could be any value between 0 and n. Or the study could be aimed at arriving on the probability of observing the first RH negative sample after m individuals are tested, where m could be any value between 1 and the population size n. Both cases 1 and 2 involve sequence of tests, each one of which is called as a trial, and results in one of the two possible, in other words dichotomous observations. Classified as success equals S when RH negative factor is observed in a given trial, or failure equals F when RH negative factor is not observed in that trial. For example, in case 1, what is the probability of observing just one RH negative factor when 10 blood samples were tested in a sequence? X equals 1 and n equals 10 in this case. Or what is the probability of observing X equals 2, 3, 4 or 10 RH negative factors in the above sequence? And in case 2, what is the probability of observing the first RH negative factor in the first blood sample itself, m equals 1 in this case? Or what is the probability of observing the first RH negative factor in m equals second, third, fourth or nth sample tested in a sequence, where n equals the population size of the blood samples? Case 1 results in a discrete probability distribution for the random variable x, where x is the number of RH negative factors observed in n samples. And case 2 results in a discrete probability distribution for the random variable m, where m is the number of samples tested to observe the first RH negative factor. Discrete probability distribution in case 1 is called as binomial distribution, and the discrete probability distribution in case 2 is called as geometric distribution. Let's dive into the details of each of these distributions. Let's start with binomial distribution first. The sequence of trials executed in case 1, which results in a binomial distribution, is called as a binomial experiment. A binomial experiment that consists of a sequence of trials is characterized by the following conditions. Condition number 1. The number of trials in a binomial experiment is predetermined. That is, n is fixed. Condition number 2. Each trial results in one of the two, in other words dichotomous observations. 1 success or 2 failure. Condition number 3. Outcome of each trial is independent. In other words, outcome of each trial is not influenced by the outcomes of the previous trials. Condition number 4. The probability of success S remains the same across n trials. In other words, probability of success in any given trial is not altered by the results of the previous trials. An example graphical representation for a binomial distribution is shown here, where the variable x, which in the example case was the number of RH negative factors observed in n samples, is called as the binomial variable, and y-axis on the binomial distribution provides the probabilities associated with each possible value of x. Let's understand the analytical details in a binomial distribution using another illustrating example. A consumer appliance store sells electric and gas-based hobs. What is the probability that 3 out of every 5 randomly selected customers buy electric hobs? In other words, what is the probability that x out of n random customers buy electric hobs? The answer to the above questions is offered by the binomial distribution, which is the outcome of a binomial experiment with n equals 5 trials and binomial variable x varying between 0 and 5. Let's start evaluating the probabilities for x in the range 0 to 5 in every n equals 5 customers. Outcome of a given trial is the kind of the hob, electric or gas, a selected consumer buys. The selected consumer buying an electric hob is regarded as success S and gas hob is regarded as failure F. The above trial is repeated 5 times as part of this binomial experiment. That is, 5 randomly selected consumers' choice of purchases are observed. For x equals 0, every one of the 5 trials results in a failure F, that is all F's. Probability of x equals 0 thus equals 5 times probability of F, where probability of F is the probability of failure for the population, which is nothing but the probability, the long run relative frequency that a customer buys a gas hob. And there is only one combination or sequence of results for x equals 0, which is all F's. For x equals 1, any one of the 5 trials results in a success S. There are 5 different sequences of results for x equals 1, which are as follows. For the first sequence alone, probability of 1 success equals probability of S multiplied by 4 times probability of F, where probability of S is the probability of success for the population. In other words, the probability that a customer buys an electric hob. The product of probabilities for 1 success and 4 failures remain the same for all possible sequences of success and failures listed above, though only the position of probability of S keeps changing. Since x equals 1 can happen in 5 different ways, probability of x equals 1 equals 5 times the product of probability of S and 4 times probability of F. Probability of x equals 1 thus equals 5 multiplied by probability of S raised to the power 1 multiplied by probability of F raised to the power 4. It can also be rewritten as probability of x equals 1 equals 5 multiplied by probability of S raised to the power x, where x equals 1 in this case, multiplied by probability of F raised to the power n minus x. For x equals 2, any 2 of the 5 trials results in successes S. There are 10 different possible sequences of results for x equals 2, which are as shown below. Since x equals 2 can happen in 10 different ways, probability of x equals 2 equals 10 multiplied by probability of S multiplied by probability of S multiplied by 3 times the probability of failure. Probability of x equals 2 thus equals 10 multiplied by probability of S raised to the power 2 multiplied by probability of F raised to the power 3. which can be rewritten as probability of x equals 2 equals 10 multiplied by probability of s raised to the power x multiplied by probability of f raised to the power n minus x. We just saw probability of x equals 1 equals 5 times probability of s raised to the power x multiplied by probability of f raised to the power n minus x, and probability of x equals 2 equals 10 multiplied by probability of s raised to the power x multiplied by probability of f raised to the power n minus x, while the product of probabilities, probability of s raised to the power x multiplied by probability of f raised to the power n minus x, is already in a generic form in the above expressions. Number of different possible sequences for successes and failures, that is 5 and 10 in the above expressions, can also be generalized using analytical derivations as n factorial divided by x factorial multiplied by n minus x factorial. Hence, the generic expression for the binomial distribution of probabilities for the binomial variable x can be written as probability of x equals n factorial divided by x factorial multiplied by n minus x factorial multiplied by pi raised to the power x multiplied by 1 minus pi raised to the power n minus x, where n equals number of independent trials in a given binomial experiment, pi is the population probability of success, 1 minus pi is the population probability of failure, and x is the binomial variable. The term n factorial divided by x factorial multiplied by n minus x factorial in the binomial distribution is represented at times as follows. Read as n choose x provides the number of ways of choosing x successes in n sequential instances or trials. Therefore, the binomial distribution function can also be expressed in any one of the following two forms as well. Often, binomial experiments are conducted on a sample of size n drawn out of the population of objects or individuals under study. Individuals or objects for a sample are drawn out of the population either by replacing the selected individual object back in the population, which is sampling with replacement, or by not replacing the selected individual or object back in the population, which is sampling without replacement. Binomial distribution function applies to sampling with replacement case, but not to sampling without replacement case. The reason being, the following two conditions that the binomial experiment requires are not met. 1. Outcome of each trial is independent, and 2. The probability of success remains the same across n trials. Both of the above two conditions are affected when sample data elements are not replaced back in the population. However, analytical studies have shown that if the sample size n is less than or equal to 5% of the population size n, then the binomial function can be very well applied to both types of sampling. If n is greater than 5%, the same cannot be applied. Binomial distribution graphs using the binomial distribution function for three different values of probability of success, 0.02, 0.05 and 0.08, and n equals 20 are shown for comparison. Binomial distribution approaches a normal distribution curve for probability of s equals 0.5. While curves that fit distributions for probability of s equaling 0.2 or 0.8 are asymmetrical, it is positively skewed for probability of s equals 0.2 and negatively skewed for probability of s equaling 0.8. The mean for a binomial distribution can be derived analytically as mu of x equals n multiplied by pi which equals n multiplied by probability of success for the population. Accordingly, mu of x equals 20 multiplied by 0.2, which equals 4, for probability of success equals 0.2. Mu of x equals 20 multiplied by 0.5, which equals 10, for probability of success equals 0.5. And mu of x equals 20 multiplied by 0.8, that equals 16, for probability of success equals 0.8. The mean for a binomial distribution is around n by 2, that is in the middle, when probability of success is close to around 0.5. Drift towards left, that is it tends towards 0 when probability of success is lower than 0.5, and it drifts towards the right, that is it tends towards n when probability of success is higher than 0.5. Similarly, the standard deviation for a binomial distribution can be derived analytically as sigma of x equals square root of n multiplied by pi multiplied by 1 minus pi. Accordingly, sigma of x equals square root of 20 multiplied by 0.2 multiplied by 1 minus 0.2, which equals 1.79, for probability of success equals 0.2. Sigma of x equals square root of 20 multiplied by 0.5 multiplied by 1 minus 0.5, which equals 2.24, for probability of success equals 0.5. And sigma of x equals square root of 20 multiplied by 0.8 multiplied by 1 minus 0.8, which equals again 1.79, for probability of success equals 0.8. The variance or standard deviation for a binomial distribution for a given value of n is highest when probability of s value equals 0.5 and lowers as probability of s moves away from 0.5 in either of the directions. Going back to the RH negative factor experiment, assume the probability of success, that is the probability of observing a RH negative factor in a given population, equals 0.23. The binomial distribution for binomial variable x with a number of trials n equals 20, that is 20 randomly chosen individuals in a given population are tested for RH factor, is plotted below. For example, the probability, that is the relative frequency as a result of repeating the binomial experiment over a large number of times, of observing 4 RH negative factors in 20 trials equals 0.207, that is 20.7% of times. And we can similarly arrive at the probabilities for other values of x as well. Binomial distribution of probabilities for variable x is shown with values in the tabular form. Suppose a binomial experiment is conducted with n equals 20 trials and the value of x is found to be 9. The probability of getting an x value as high as 9 equals the sum of probabilities of x between 9 and 20, including 9 and 20, and that equals 0.246. In other words, 2.46% of the times. Since probability of getting an x value as high as 9 is as low as 2.46%, the above observation should cast doubts on the assumed value of probability of success for the population, which is assumed as 0.23. Maybe probability of success is much higher than 0.23, given that we got a value 9 for x. This above example illustrates how binomial distribution can be put to use to verify the assumptions, in this case the assumption with respect to the probability of success for the population is made. That brings us to the end of the study on binomial distribution, and let's now focus on the other distribution, namely the geometric distribution. In general, the geometric distribution is a discrete probability distribution for the random variable m, where m is the number of trials conducted before the first success is observed. The first success can happen in the first trial, or second trial, or third trial, and so on, or in the n trials, where n can theoretically tend towards infinity. What is the probability associated with each one of the above cases is provided by the geometric distribution. Like in the case of a binomial experiment, the experiment involving geometric distribution shall satisfy the following conditions. Condition number 1. Unlike in the case of binomial experiment, the number of trials is not predetermined. M is extended until the first success is observed. Theoretically, M can tend towards infinity. Condition number 2. Like in the case of binomial experiment, each trial results in one of the two dichotomous observations, one success or two failure. Condition number 3. Like in case of binomial experiment, outcome of each trial is independent. Outcome of any trial is not influenced by the outcomes of the previous trials. Condition number 4. Like in the case of binomial experiment, the probability of success S remains the same across all trials. Probability of success in any given trial is not altered by the results of the previous trials. Geometric random variable x, note the notation m is changed to x, equals the number of trials until the first success is observed, including the success trial. The discrete probability distribution of x is called as the geometric probability distribution. Let's this time conduct the experiment with sequence of trials aimed at observing the first RH negative factor. Accordingly, the number of trials x each time the experiment is conducted is a random variable and may range between 1 and the population size n. The sequence of outcomes for each value of x shall be S, F, S, F, F, S, F, 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 S, and so on. The probability of x for each value of x shall be probability of S, probability of F multiplied by probability of S, probability of F multiplied by probability of F multiplied by probability of S, and so on. Assuming the probability of S, that is the probability of observing an RH negative factor in any given trial, is 0.23, which is nothing but the population probability of success. We can evaluate the numerical values for probability of x for each value of x by substituting probability of S as 0.23 and probability of F as 1 minus probability of S, which is 0.77, in the above table as shown. The generic equation for evaluating the geometric distribution for probability of x can be derived from this column. Accordingly, probability of x equals probability of f raised to the power x minus 1 multiplied by probability of s. It can be rewritten as probability of x equals 1 minus probability of s raised to the power x minus 1 multiplied by probability of s, which in turn equals 1 minus pi raised to the power x minus 1 multiplied by pi, where pi is the population probability of success. Geometrical distribution of probability of x in the above table is graphically plotted as shown. Probability of x in a geometrical distribution reduces with increasing x. Probability of x is highest and equals the population probability of success for x equals 1. That is the first trial. Probability of x reduces continuously thereafter. Steeper is the fall with increasing values of pi, in other words, probability of success. Some additional examples of probability calculations using geometric distributions. Probability of observing the first RH negative factor within the first 3 trials equals probability of 1 plus probability of 2 plus probability of 3, which equals 0.543, which is 54.3%. Probability of observing the first RH negative factor between third and the fifth trial equals probability of 3 plus probability of 4 plus probability of 5, which equals 0.322, which is 32.2%. That brings us to the end of the session on binomial distribution and geometric distribution. We understood the context behind these topics and subsequently the requirements, underlying concepts, mathematical functions, and their usage with some real-world examples. Thank you for watching. Please leave your questions, remarks if any, and I'll revert back as soon as possible. See you with the next topic, and bye until then.